Steinhauer here, welcome back. Continuing our discussion of telescopes. And now I want to ask you the question, if you had a bunch of money, let's say $10 million to build a telescope, where would you want to put that telescope? Give it some thought, write down some ideas. We'll talk about where we actually want to put the telescope. Okay, so the question is, where are good places to put telescopes? Well, one of the things you want to think about is, do you want to put it in a city? Do you want to put it in somewhere rural, and why? Well, it turns out that cities are rather bad places to put telescopes. Why is that? Well, it's a problem that's becoming worse and worse as the decades roll on, and that is a problem of light pollution. Here's an example of how bad the sky looks from increasingly brighter and brighter areas. So on the left, we have the inner city, and you can see almost no stars. If you were to look up in Manhattan into the night sky, the sky is so bright from all the lights that are around that there are virtually no stars in the skies at all. Even as you move away from the big cities into the suburban, urban transition, again, very few stars available to you simply because the sky is so bright. It's not that the stars aren't there, of course. It's just that the sky is much brighter than those stars are, which makes it very difficult to see them. As you move to darker and darker sites in the suburban skies, you see more and more stars. Even here in Geneseo on campus, you will see far fewer stars than you would if you just take a walk down onto the valley, say down into near the airport. So the further away from city lights you get, the better you can see the sky. And in fact, if you've never been to a very dark site, you owe it to yourself. Go on some warm summer evening to a very dark site away from all other lights. And in fact, there's some national dark sky sites where outdoor lighting is prohibited within a rather large area, and the difference in the sky is unbelievable. You will thank me for this. Take a friend, go out and just look at the sky. It is a completely different experience than even out here in rural Geneseo view of the sky. Looks completely different. So obviously, if you're going to build a $10 million telescope, you don't want all of this light pollution mucking up your sky. And in fact, there are professional observatories that were built in the 1900s that are completely unusable now because they are so close to cities. The Yerkes Observatory, I said in the last video, was near Chicago. That's an unusable site now for professional astronomy. We'll talk about Edwin Hubble. He did his work in the 1920s at Mount Wilson Observatory, and Mount Wilson Observatory literally overlooks the city of Los Angeles. It is now a site that is unusable for any professional astronomy. So these sites are getting fewer and farther between, but they do certainly still exist. You want to build your $10 million telescope well away from city lights. Another thing you want to do is to get away from the atmosphere as much as you can. Here are two examples of a same part of a galaxy, one taken from a ground-based telescope and one taken from the Hubble Space Telescope. And so you can see, what does the atmosphere do? The atmosphere actually is a blurring effect, has a blurring effect on the light that comes through for various reasons, but mostly there are turbulent cells in the atmosphere that kind of act like lenses, but they're not lenses in helpful ways. They're just lenses that distort and move around the image of the thing that you're looking at. It's kind of analogous to observing the universe from the bottom of a swimming pool. If you've ever dove down to the bottom of a swimming pool and looked up, everything's blurry, and everything's not only blurry, it's moving around, it's wavy. And that's exactly what happens to the sky. And in fact, this is why stars twinkle. If you go out at night and you look at stars and they're twinkling on and off, that's not really the stars doing that. That is the effect of the atmosphere, not only moving those stars around, but causing it to turn on and off as that light travels in different directions and gets held up and released. So the atmosphere only hurts you when you're building a telescope. And so if you're building a telescope and you're spending a lot of money on that telescope, you're going to want to put it above as much of the atmosphere as possible. And it turns out simply moving your telescope to the top of a mountain gets it above most of the atmosphere, as long as it's a tall mountain, gets it above most of the atmosphere that is blurring your target. So putting your telescope on a high mountain helps with this effect. Not only does it help with the blurring, but the atmosphere can actually absorb some of that light that's coming in. And of course, you don't want that either. The higher you build your telescope, the less you have to deal with atmospheric blurring and atmospheric absorption as well. So that's important. You want to build it on a remote, high mountaintop. Here is an example of such a remote, high mountaintop. This is the summit of Mauna Kea in Hawaii. It's at 15,000 feet. It's not the highest mountain in the world, but it's one of the highest accessible mountains in the world. And it happens to be at a very good site in terms of weather as well. It's rather dry on the top of Mauna Kea. And that's important because you don't want it to be raining all the time, because when the clouds roll in, you can't see anything that you're looking at. And you can see in this particular shot of Mauna Kea, you can see the clouds are actually below the level of this mountain. And so sometimes, even when it's cloudy at the base of Mauna Kea, in Hilo or in Kona, it is not cloudy on the top of Mauna Kea. And these telescopes that are some of the biggest and best in the world will still be able to operate and be able to see the sky. In fact, some of the telescopes we've been talking about already are here. These are the two Keck telescopes. These are both 10-meter telescopes, segmented in hexagonal segments. This is the Gemini telescope. I believe it is the 8-meter telescope mirror that we were looking at in the last video. This is a Subaru telescope, another 8-meter diameter telescope. So this is one of the best sites in the world to build a telescope, and they are now, in fact, building on this mountaintop the next generation of telescope, a 30-meter telescope. The TMT, the 30-meter telescope, will be located on this site in the summit of Mauna Kea, because it's one of the best in the world. Okay, now, obviously, it's even better to put a telescope in space, but obviously it's way more expensive. This is a picture of the Hubble Space Telescope, probably the most famous telescope in the world. And it does so well, not because it's the biggest telescope, it's not. The Hubble Space Telescope has a primary mirror that's located about right there, that is about 2.5 meters in diameter. That's way smaller than the ground-based 10-meter telescopes. But it is even higher above the atmosphere. It is above the atmosphere altogether. There is no blurring effects at all. There is zero absorptive effects at all. And the Hubble Space Telescope beat all of those ground-based telescopes for decades because it didn't have to worry about that atmospheric blurring. It could get the clearest pictures possible of any telescope that existed at that time. We've developed techniques now to do almost as good as the Hubble Space Telescope from the ground, and so it's not really as necessary as it used to be to put telescopes in space for that reason, and it's still way more expensive to put a telescope in space. I talked about $10 million for a telescope. That's going to build you a medium-sized telescope on the ground, but it's not even going to be able to lift anything into space, really, that's useful. The Hubble Space Telescope was a $2 billion operation. The next generation of telescope that's going to be launched, the James Webb Space Telescope, will be is a $10 billion enterprise, right? So to get a telescope into space, you really have to have a good reason to do it. So we know that the blurring effects of the atmosphere is one of them, but there's also another really important reason to put a telescope in space, and that is the absorptive effects are not wavelength independent. So here is an image that shows there's a lot going on here. So let's try to figure it out. On the top, we've got a bunch of different regions of the electromagnetic spectrum, if you remember. From short wavelengths to long wavelengths, we've got the entire gamut here. from gamma rays to X-rays to ultraviolet to visible to infrared to microwave to radio. All of the entire electromagnetic spectrum is here. And these lines that are extending down, this is supposed to be the top of the atmosphere at the top. And of course, you've got the ground on the bottom. But the lengths of these lines represent how far into the atmosphere a typical photon that is in that wavelength regime will travel before it gets absorbed by the atmosphere. It is how transparent is the atmosphere to those particular wavelengths. The longer the line, the more transparent it is, the easier it is for that light to reach the Earth. You'll notice there's a couple of nice windows, and the visible light spectrum is one of them, right? The atmosphere is very transparent in visible light. Almost none of it is absorbed by atoms in the atmosphere. One of the reasons why our eyes work in the visible part of the regime is because, one, the sun is emitting most of its light there, and two, it bounces very easily around the Earth and is useful for seeing things. Our eyes are adapted to see at those particular wavelengths. There's another window in the radio where the atmosphere is very transparent and easy to see from the ground. It's not true almost anywhere else. For very, very short wavelengths, gamma rays, these almost all of them are absorbed before they reach the ground. X-rays are even worse, and in the far ultraviolet, it's even worse. They just don't penetrate very far into the Earth's atmosphere. And this is a good thing. There aren't many of these gamma rays running around, but there are a few, and they're extremely harmful. They're highly energetic photons. If they hit you, they would do damage to your cells. And so the fact that the atmosphere shields us from those, and X-rays, which are also damaging, and even far ultraviolet, which are also damaging, is a good thing. This protects us. It's probably allowed life to evolve in the way that it has, that our atmosphere absorbs these photons. So that's a good thing, but it's a bad thing if you want to study the universe at those wavelengths, right? You can't put a gamma ray telescope on the ground because it will never see anything, because those photons never reach the ground. You can't put an X-ray telescope on the ground, even on a high mountain, because those X-rays, 99.99% of them will be absorbed before they reach your telescope. And that's not a very useful thing. Even here in the infrared, it's not quite as bad, and it's patchy, but there are regions where you can't, the light from in an infrared regime just doesn't make it to the Earth. And so you need to build a telescope that is either flying in an airplane, and there are actually infrared telescopes that are mounted to airplanes that will fly in the atmosphere and take images from the airplane, or put them into orbit around the Earth, and then you don't have to worry about any of this stuff. And so there are gamma ray observatories, there are X-ray observatories, and there are infrared observatories, but they are in space. They have to be in orbit because you just won't see anything any other way. So that's important. That's the other reason why you would spend a lot of money to put a telescope in space. Not just the blurring effects of the atmosphere, but the absorptive effects of the atmosphere. Why do we care about observing the universe in gamma rays or X-rays or the infrared? Let me just show you a quick example of the same region of the sky seen in 3 different wavelengths. So this is the constellation Orion. Here are the 3 belt stars. Here's the Orion Nebula right below it. Here is the red star Betelgeuse. Here's the blue star Rigel. This is a constellation that's visible in the southern sky in the wintertime, if you go out just after sunset. And this is what it looks like from the visible part of the spectrum. The middle section, is exactly the same region of the sky seen in the X-ray part of the spectrum. And the colors aren't real, but the blue represents higher energy X-rays and the red represents lower energy X-rays. And so you can see you're seeing completely different things, right? The Orion Nebula is gone. You can't even see it here. And these things that are bright in the X-rays don't correspond to anything really in the visible part of the spectrum for the most part. What are these things? We'll talk about them later. These are usually very compact, high energy objects. Things like neutron stars, things like white dwarfs, things like black holes that are generating large amounts of very energetic photons that are not visible usually at all in the visible part of the spectrum. You just learn vastly different things about the universe in the X-ray than you do in the visible light. And the same with the infrared. Look at this thing over here. This entire region of the sky is glowing in the infrared. What are we seeing here? We're seeing the hot gas and dust that makes up the interstellar medium. And you can see these are regions where stars are being formed. And you can see the Orion Nebula is a huge, bright, glowing dot of infrared glowy gas. And you can see the leftmost star of the belt is also a very not high intensity knot of infrared emission. But this whole region has infrared emission all over it. Some of it more diffuse and some of it more concentrated than others. So you learn, again, fundamentally different things about the universe in the infrared than you do in the visible or the X-ray. So we're very interested in learning, of course, everything we can about the universe. So these infrared telescopes and these X-ray telescopes play very important roles in understanding different kinds of objects that we see in the universe. Here is just a quick example of some of the telescopes that we have out there. So we've got the electromagnetic spectrum, the entire electromagnetic spectrum down here, from gamma rays at the short end to radio waves at the long end. I want to point out that this isn't really the rainbow, right? The things that we would see as red and yellow and orange and green and blue and infrared and indigo and violet are all visible light photons, right? But we can sort of represent the entire electromagnetic spectrum in this way because radio wavelengths are the longest wavelengths and red is the longest wavelength for the visual part of the spectrum. And so you can sort of think of this as a continuum, not in color, but of wavelengths. And so there are telescopes that are in space. These are all space telescopes that are designed to look in each of these regimes. The Planck telescope is mapping out the radiation that is reaching us from the remnants of the Big Bang. The Herschel telescope is a far infrared. The James Webb Space Telescope hasn't been launched yet as of the making of this video, but it will be a sort of the replacement for the Hubble Space Telescope, which is a visible ultraviolet, except it will operate in the near infrared instead. The Gaia telescope is operating, measuring positions of stars very accurately. Obviously, the Hubble Space Telescope is operating the visible, but also in the near ultraviolet part of the spectrum. And then we've got a couple of high energy telescopes. XMM Newton satellite is an X-ray satellite, and the Integral satellite is operating and looking at the universe in gamma rays. So it's important. We need to be able to monitor the sky. We need to be able to study objects in all of these different wavelengths because they tell us fundamentally different things about what is going on in the universe. And that's really important. Okay, thanks for stopping by.